All right. So here we go. Right. I'm screen sharing. I'm recording, and let us go back a little bit to the last time. Okay. This is your typical formula. Okay. Um, one represents the response, right? The virtual internal response to the unit load that you attach to the structure. Another is the actual deformation coming from the actual load on your structure. Okay, so that is the formula. So without further ado, let us take a look at the formula. You need to take a look at anything, you let me know. Okay, so here's the example. Okay, forgive me for not fixing this. So could you please change this first? Okay, there's some minor mistake in the document that I give you. The third member, CD, it should be FG. The fourth one should be GH. The fifth one should be DE. And the sixth one should be CD. Okay? All right. Let's get that first. You cannot see? FG, that's FG, GH, DE, and CD. All right? So first thing first, because judging from the formula that you just saw, that we just revisited, you know that you need to actually analyze the structure twice. Let us see this again. You see, there is the virtual internal response, which is the force in your member according to the virtual load. Okay, so there's a force in each member according in response to the virtual load, and there will be the force in each member due to the actual load. So now I hope that you could see that we need to analyze the thrust twice for the internal forces. For the internal forces, one internal force is due to the actual load, because we are going to use that to calculate deformation of each member. Okay, another is the force in members due to virtual load to obtain the internal virtual response. Okay, 2 times or twice. Okay, so first here is the we can always make notes. I'll try to write as much as possible so that you get everything. So this is the first one. Okay, analysis of internal forces for calculation of internal work. Let's say internal displacement. Okay, that's more to the point. Okay, and now because our system consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 members. Yes. Oh, okay. Yeah, like we right. I should have known, right? But I never learned, do I? Wow. And then I blame students for making mistakes, right? I keep making the same mistake. Wow, inexcusable. Anyway, so this is for the calculation of the internal displacement. So you must know that for internal work, what symbol do I use? Hang on. I didn't use anything, right? Yeah, internal work. So internal work, you have to sum up every member. So I begin from 1 to 17, right? Because we have to sum up the work of every member that forms this trust. So we have I count correctly, 17 members. Okay, so I'm not going to go through this because it's a same old thing from static, but I give you the result right away that this is the internal forces of each member after the analysis of the actual load case. Okay. So you must know that this is the actual load case. Okay. So you see that after the analysis, member AB is actually zero force member, you see. And DE, yeah, that's another one that is also zero force member. Okay. You can look at joint A and you realize that member AB cannot have a force. Otherwise, if there is a force in member AB, your sigma Fx can never be zero. Because there's just one member in the inclined angle, so that produces the horizontal load. There is no second member to help to produce the horizontal load. So AB force in AB has to be zero. Simple as that. And you could look at joint H. That's pretty much the same. See, GH and HI will can balance each other out, but there is no other vertical force element. So CH will have to be zero. There. And we have more. BG, that too will be zero. That one will be harder to tell, but after the analysis, you know it's zero. So now we know that, for example, member AB, BC, will have the force equal to 41.2 tons. The minus sign here represents compression. So you have to understand by now that the direction has impact on the work. So you must be mindful of the direction of the force as well. Let's say if you have compression on member BC, but member BC itself is shortened, you have compression and member BC is shortened. So that means the compressive force moves in the same direction as the displacement of the member. So that is a positive work. But somehow if member BC is elongated and you know the force is compression, but that the force travels in the opposite direction as the displacement, but that's a negative work. So right here, what you can tell is that this is compressive force, so member BC is shortened under the actual load, correct? And if I may elaborate on this a little bit, you would know that if you want to calculate the work of member BC, the work is NL over AE, right? And now if I say we have the constant A and E, we can exclude this from our calculation. And you know, after you sum everything, you can divide your summation by A and E if it's constant. So I could just say right here that it's 1 over AE and it's NI multiplied by LI. Correct? Or I could just say, okay, the work of member, I'm sorry, not the work, the displacement of member ABC is compression, and it is equal to 41.23. It's tons, right? You can include this here or later because everything is in tons. Multiply by the length. You want to maybe multiply by 100 and then divide by AE. You can do it now or you can do it later because every member has AE. So this is the displacement, just the displacement of member BC. Okay. Now, are you still with me? So thank you. So this I elaborate on this a little bit just to show you that we analyze this structure under the actual load so that we can have information to calculate displacement, actual displacement. Okay. Now, in order to get the work, we need the internal response due to virtual work. So what do we want? Mid-span deflection, vertical deflection. So what we need to do to get this is to vertical deflection and mid-span. So you need to have the virtual work at that location in that direction so that that virtual work will produce work. So every year, someone will not pay attention and apply the force either in the wrong location or in the wrong direction. It's very sad. Here you see we need to know vertical deflection. So if you could go back here and see the equation for the work here. In order to get this term, you need to apply the unit load to multiply with the displacement that you're looking for. So it has to be yeah, it's a red one, right? Right here. Sorry, here. It is applied at mid-span in the vertical direction because displacement here is what we needed to know. So we apply that unit force at that location in that direction. And after the application of the force, remember this is virtual. What do you like for virtual? Maybe pink? Okay, so this is virtual. So let me try to use the same kind of sentence. So this is number 2, analysis of internal response say with respect to whatever due to, that's fine, due to virtual load, virtual unit load. Okay, so here's the key is virtual. So you apply that and you start performing the same analysis, but only this time your load is this virtual load. So what you have here is the internal load for each member corresponding to the fact that your structure now has this virtual load. Okay, so again, AB0. And here, for example, is minus 0.687, so on and so forth. Okay. Oh, you know what? I kind of like the microphone in the other room because I can put it in vertical direction like this. It stays. Here, now something very roller. No, it's a bit difficult to put it upright. So I have to hold it all the time. Anyway. So, any question? Are we okay on this? The concept is only this: the actual load case and the virtual load case. And if you know how to apply the virtual load, the rest should just fall into place because I have to assume that you guys can handle the plus, right? Let's hope so. Yeah, let's hope so. Give me. I'll go back a bit. Okay. Virtual load case. Oops. Okay. So now, let's say if I talk about the internal work now. I can say, oh, one more thing. You see, before I go, notice the force. This type is minus for compression as well. So that means the internal force in with respect to this unit load is also compression. Here is compression, you see, and here for this is also compression, which means that the member is shortened. So it's a positive work in the end because they go in the same direction. So here the sign could help you, because if compression meets compression, it's minus multiplied by minus, it becomes plus in the end. Okay, so be mindful of the sign you use, which means, yes, it is important that you identify the type of force that you have. So when we talk about the work now, it's going to be this term, right? Multiplied by the force of the member, but it's a virtual. So this term is the displacement. See, this term is the actual displacement of the member. If you multiply that with say it's in, oops, sorry. From that, it's NL over AE, which is the displacement, the actual displacement due to the actual load. Now you multiply this with your virtual response. So you have work of one member. And you need to do this 17 times to get the internal work of the system. Okay. And here, coming from above, we have I wouldn't remember. So I need to go back. I don't want to copy because a problem occurs every time. 41.23. Okay. Why? Oh, you see it, but actually I restart my iPad. Okay. So that's NL. Why? Sorry. See, that's the beauty of using iPad, right? If it happens on the whiteboard, I have to erase everything because I couldn't cut paste in my real life. So anyway, 2.06 multiplied by 100. Okay, and this because I like to change the unit into centimeters because we have AE in centimeters. Thank you for asking. I thought I might say that again, but you know. And now I have this coming in. Oh, I have to have the minus sign here, right? Indicate compression. And now here is minus 6.687 and divide by AE. So the pink term is the internal response due to the unit load. The blue term is the internal displacement due to the actual load. So, you know, in the end, you would know that you can create the table, but I just want to get the concept straight first. Internal response due to unit load, virtual load. So the ping load itself is also virtual. Okay, here is the internal displacement due to actual load. Okay. Remember that this is just for one member, and you need to account every member so that it's a work of a system. All right, any question? So the key thing is to perform the proper analysis on the trust. The rest is just simple arithmetics, right? And it will come a time when you need to be accurate on your calculation, because you cannot say I make mistakes on calculation because I was not very focused. I couldn't concentrate. The family around my house, they having a fight. Something like that. The husband and wife, they had a fight. Very near my house, so I couldn't concentrate. There will come a time when you need to be accurate, precise in your work. And I have to say, sadly, that I just started grading the homework, so I found that some students still could not calculate the reactions. Wow. Let's hope that it's up you, right? Because when you mess up the reactions, the rest is useless. Because you give yourself the wrong equilibrium for the entire structure to begin with. But the rest is no use. And I told you that when you calculate the reactions, take moment twice to check. Some took once and wrong. The rest just it went down the toilet just like that. Some took it twice, but never checked, which is sadder. Because they listen to me, but you should have known, right? That when you take the moment twice, at least you just check with the force. Whether you sum it up, it's equal to the external force. Super very sad. But it's our job. It's the instructor's job to eradicate these kind of mistakes from you. So that's why you're going to get harsh homework score to remind you that you're still pretty bad at this, and you need to make a step backward in order to move forward. Just like rugby, the only way to move forward is to move back. Very classy. So you wonder how, right? Yeah. Anyway, so after we do this, I separate the two tables. So this is basically the table for the internal response due to the virtual load. This is the table for the response for the actual load. Okay, and you can notice from this calculation here that, or this formula here, that you need to sum up every member in the system. So that's why we can create a table, sum it up. Okay, and one more thing before we move on, I also include the second case, that is a calculation for excuse me, I didn't mention this, the horizontal movement of joint J. So in order to get the horizontal movement of joint J, we need to apply the horizontal unit load at J. And it becomes very easy, because if you notice, if you are pretty good at statics, here gives you the concentric force, right? So all the forces should be in the bottom chord only. So yeah, the response to this is just force equal to 1 in the bottom chord member. The rest is 0. Woohoo, like that, right? So now, after you can see the concept, we can just assemble this, or there's no need to do these 2 steps if you can see where you are headed. So in the end, here it is. Okay. And as I mentioned before, this comes from the fact that we can put AE out of the sigma, because it is a constant, and we can just include that the end to help reduce our tedious work. So 1 over AE is out, and here is I from 1 to 17 of, here we go. Forgive me for this, because I change the symbols according to my emotion for the time. So here F is for the actual force, okay? I don't know why I do that. And here is the virtual. But as long as we understand, symbol doesn't matter, does it? You can use the sun, the moon, or the stars, the comet, flowers, trees, dolphins, eagles, whatever, if you like it. But you'll spend a lot of time drawing the star every time. But this is easy. So here it is. You put the actual the response to the actual force in there, and the response to the virtual force in there, and multiply them in the end to get that term. Okay, so it's Fi, Ni, and Li. Sum them up. Okay, so there it is in the end, and that's the result of your summation. See, I multiply them in the end. So now you know 10 to the power of 3 represents the force in tons and change into kilogram force, and 100 represents the change of the length into centimeters. That divide by the constant in this case, which is EA. So here we are with the deflection linear. So please recall that this is in fact, let me back up a little bit. Right here I use, maybe, okay, I should change this a little bit, right? So that just hang on a minute. I want you to, I never mean to hurt you in this way. So that let's change that into F. Okay. So here is F and N. Okay. So you see, what you just saw from that table is in fact this term. See? Right? So instead of doing this every time, we can create a table and let the spreadsheet do the work. But in the exam, wow, it's hand calculation. We have to be a little bit smart doing that. Okay, so give me one more time. I need to scroll down to show you this. So just pay attention to what we have in the green cloud. Okay, what we have in the green cloud is essentially this term. And the simple the calculation that we have made is simply this one. So this one should be equal to minus 0.687 multiplied by 40. Is that 40? 41? Yes, 40 or 41. 41.6 something. 0.22. Okay. And the length, which is 2.06. You should get that number. Okay. You do that, sum it up, we get the deflection in the end. And again, the sign matters. Positive number means, can you guess? We are calculating the deflection, right? So we should not talk about tension and compression. It's work in the end, correct? So positive work, what does it mean? Your friend says the positive number means the some kind of the keyword is same direction as what? As what? Same as what? Okay, he's got it. I know he's got it, but he has to spend some time, arrange his words. So positive number means the displacement. Sorry. Oops. I didn't mean to drag that along. Positive number means this actual displacement, which is our target, right? Actual displacement is in not enough space. The same direction, that's my direction, as the virtual. I can't believe this. On time. As your virtual unit load. Okay, that's work. Your force travels in the same direction as the structure, so it produces the positive work. If it travels in the negative direction, it means it's a negative work. And the direction of the virtual load is opposite of the direction of the displacement of the member. Okay? So you can fill in the blank by yourself. Negative means actual displacement is in the opposite direction, right? Okay, so that's it. The use of the virtual work to calculate displacement in the truss. Is there any question? You see, it's why are you touching? You see, it's not difficult. I just want to know. I'm not saying that you're wrong or anything. I'm just curious, okay? Anyway, right. Where were we? Here, right? We have gone. So that's it. If you understand what you need to do, okay, and I think it's pretty useful. Okay. Now, the next example is just the same. It's just more work, and you know that you spend most of your time analyzing the truss. And let me tell you now that I never intend to review the truss view because you've done it before. It's your job to refresh it if you feel like, I need to do this, I don't remember anything. So it's your job. Be responsible to dig deep in your lost memory, to handle this situation. And this when you assemble everything together, it's pretty easy. So you should realize that you would spend most of the time analyzing for the internal forces of the truss in both load cases. That's the thing. So here, if we are going to measure your ability to do this, it would mean that you would spend the energy doing the old knowledge, taking care of the fundamental from the previous task before you can get to use this knowledge. That's gimmick enough. And I don't know if we can. Oops, not that. That's a homework. Oh, we have a lot of things. Okay, no. here. You see, virtual work on trust now can analyze the internal forces under the actual load and virtual load. That's 40% each. So I'm pretty generous here. That okay, this is your own knowledge, and if you could take care of one case, that's 40%. Another that's 20%, and the assembly will account for just 20%. Maybe I should reduce the first two, right? But it's a lot of work, so I give a lot of credit for that. Okay, so let us go back to the example. Yeah. So that would mean here is 40%, right? Of the work. Here is another 40%. And the final assembly here, you know, all this hula baloo to get to the final result, and then this just 20%. Okay. And we still have 5 minutes, and we can revisit this a little bit. Here is the same thing. We need to do essentially the same thing, but with different structure. So I don't think I need to go through all this. I'm not sure if we have the solution for all this problem available in the video clip from last year. It may be there. You know, you could revisit that, or you know, if you want to do some exercise, all the forces here are given for you. See, that's the actual, right? Says here again, mid-span vertical deflection and horizontal movement of joint L5. So here would be, you know, you need to apply the load there to get the vertical displacement, okay, which leads to this calculation, okay, and another one is the horizontal movement of joint, L5, horizontal L5, so you apply horizontal force, L5, and the response is this one, okay. And, you see, if I go through this, it's, you know, statics all over again. I don't need to. You have the actual load case, you can analyze for this. You have the virtual load cases, right? And you have to analyze for that. In the end, you perform the same task, and here we go. That's the answer. So that's it. You know, how could I come up with a trust like that? I perhaps took this example from some textbook, I don't remember, or some exercise in the textbook. I solved it. But the point is, doesn't matter. As long as you can analyze the trust, the rest should fall into places. If you're going to have trouble doing this, you're going to have trouble in the analysis of the internal forces of the trust. And I can see every year that some students cannot use the method of section. Yeah, you cut the section. Because in method of section, you need to know where to. When you look at member, for example, if I want to calculate the force in this member L1, L2, I can use method of joint, or I can just simply cut the section here and take the moment there very quickly, right? That's it. Or, you know, you get to the member in the middle like this. Here, to get L2, L3, I can just cut it here. And then take moment at this U2. I get L2, L3 immediately. But most of you will just keep going from joint L1, U1, L2, U2. Oh no, it takes 2 hours already. Like that. And I think trust is, say, the most basic structure you learn to equilibrium. So to repeat it here is somewhat slightly embarrassed. Okay, so we don't need to do this. We are grown ups. So is there any question? Your question should be something like, come on, will it get any harder than this? This is too easy for me. I'm bored. Why do you keep telling me some easy stuff? I thought your class would be challenging in terms of, giving me, a mountain to climb or something like that. And in so far, it's just like, trying to swim in the bowl. Too easy. But you can drown in the bowl too, right? Just very sinister laugh. Anyway, so it's a 1 minute before the break. So let's take an early break, 10 minutes. If you don't have any question, we come back about 10:30. Okay. Um. Oh no. I want to stop the recording.